Good evening. This is the lecture series of A-level chemistry, and today is lecture number 45. We'll be talking about amines, amides, amino acids, and proteins. This slide we discussed in the lecture 44, but it was to be discussed a little bit more, and therefore I'm taking the last slide of lecture number 44 too. And when we talk about amino acid, it's an important group of compounds that contain two functional groups. One is this amino group, another is carboxylic group. So here is a general formula of amino acid. General structure, and we call that 2-amino carboxylic acid. The structural formula, we write it like this. Okay. And then we see this amino acids are amphoteric. What we mean by amphoteric? That it can act both as an acid and also as base. Since it has an amine group which is acting as a base and acid group which is acting as an acid. So this amino acid is the building blocks that make proteins. You know, there are about 20 naturally occurring amino acid proteins, amino acids. The simplest one, this is the simplest one. In place of R, we are having an H, hydrogen, and that's what we call glycine. And the systematic name is amino ethanoic acid. Okay. This R could be an acidic group, it could be an amine group, it could be an alkyl group. So if it's an acidic group, then it is an acidic basic group as amine group, and then neutral alkyl group is a neutral. It is neither acidic nor basic, it's neutral. Next, we talk a little bit about reaction of amino acids. And undergo most reactions of amine and carboxylic acid. However, each molecule can react within itself due to its basic amine group and its acidic group. And ion form, we call it Zwitter ion. It comes from German word Zwi, that means two. So it can be charged as positive ion, can also be charged with negative ion. You see that now. If we react, and then we can have a positive ion here and a negative oxalic acid. That's it. And amino acids are crystalline solid, okay, and that are soluble in water. The solution of amino acid in water contains glutathione, as I said already, and that can resist change of pH. And how? If we add little bit of alkali acid or alkali, we see there is no change in pH, and that what we call half-hour solution. So pH is lowered by an acidic group that of the Zwitter ion will accept an hydrogen ion, acidic group, and hydrogen ion, and then we can get this cation. And from that cation, if we add an hydroxyl ion, we get this anion. So as I said, by adding by adjusting the pH of small amounts, we can reach a point where neither the positive nor negative ions show about dominate. So the pH is called the isoelectronic point of an amino acid. This isoelectronic point can be found by measuring pH value of amino acid, and that solution when it is not attached to either a positive electron or a negative electron. Okay, we can make amino acid. From amino acid, we can make peptides and proteins. As I said, peptides are compounds that made by linking amino acid together in chains. You see, this is an amino acid. This is an amino acid. We link together, and this is alanine. This is glycine, and then we can have this compound alanine glycine. And here is the peptide bond. This is the peptide bond. So this is the peptide bond. And we reacting this together, we can eliminate mole of water and forming the peptide bond. This is how we form peptide bond, as you said, and peptide bond or peptide link. Biochemists call this peptide bond or peptide link. Okay. This is also, we can call a condensation reaction. Condensation reaction, that means that small molecule is being released during the reaction. So here it is a peptide, and then if we make reflux into acid, that is acidic refluxic, then we can get this cation and this cation, and then add water to it, and then we get this alanine and glycine and protein also. When proteins and peptides hydrolysis, that's what I say. We are doing hydrolysis in acidic condition, and then cation forms, and then these are converted into alpha amino acid on dilution with water. Okay, next slide. We can show that a human body, we are talking about proteins in human body. So how many different proteins we do have in our body naturally form? Here is made of protein. If we take these, the surface of skin is also made of protein. If we take this, enzyme amylase found in salvia in protein. And the hormone insulin is a protein made by pancreas. The hemoglobin in blood cell is also a protein. And then if we continue, the fiber of nerve cells are surrounded by protein. The muscles fibers are made of protein, and bones consist of minerals embedded in collagen, which is also protein. And this is also muscle to bone, which contain protein. Two nails and fingernails are also made of protein. So proteins in human body, there's a pictures of proteins in human body. Okay, here are about 6 protein. We said that we do have about 20 natural occurring protein. So lysine, and that is R side is the abbreviated name is glycine, and this R side is H, and then alanine. This R side is H, this is alanine. The R side is H3, alkyl group, and cysteine. R side is CH2SH, and then this is phenyl, the phenylalanine, and serine, alanine, alcohol side, and then acidic side, glutamic acid. That is the abbreviated name of this. We have aspartic acid also, protein. Okay, then we go to the next slide, and there we talk about polymerization. A little bit about polymerization, condensation polymerization. And then what you say, let's say what is polymer first. We have been talking about polymer in organic chemistry also. And then we saw that small molecule is linked together and having a chain, and that's what we call polymer. Here you can see that this is a compound, this is a compound, this is also compound. We linked all this together, and then we are getting this long chain, and we call it condensation polymerization, because every one, this is water molecule coming out, this water molecule coming out, and this water molecule coming out and forming this chain, and it is also known as nylon 6,6, because you see there are 6 carbon atoms in this. There are 6 carbon atoms, and therefore the polymerization we get, this is called condensation polymerization, and we got nylon 6,6. Okay, we can have another polymerization, that this is polypeptides, protein link. And then we can have a synthetic commercially important nylon, we say, and then in hexadiol glycuride in hexacyclohexane. This is, and then this is also the hexacyclohexane product. And that these together form a polymerization, condensation polymerization, with leaving a small molecule of hydrogen chloride. So when a condensation polymerization happens, we get long chain of carbon hydrogen, and then this is polymerization from monomer to polymer. This unit is the monomer unit of this polymerization. This unit is the monomer unit, and then we get the small molecule out, like says I said, water or hydrochloric acid. Okay, and then we go for we compare addition polymer and condensation polymer. What is addition polymer? That's what we discussed in lecture 30, and now I'm just telling it again. Condensation polymerization will result the formation of long chain organic molecule known as polymers from relatively small organic polymers, which is known as monomer, as I say. But these are some clear differences between two processes: additional polymerization, and condensation polymerization. The type of reactor visit, addition polymerization involves only addition reaction. And what happens after polymerization? We do get a release of water molecule or hydrochloric acid eliminated from the chain and split off. The type and link of this polymer chain, in addition polymers, the central chain consists of carbon atoms and carbon-carbon single bond. In condensation polymer, the central chain consists of short aliphatic or aryl section linked by ester groups or amide groups. Type of monomer involved in addition polymers, the monomers have molecules which carbon-carbon double bond, and in condensation polymer, the monomers have molecules that are at least 2 functional groups, which may be of same or different functional group. The condition for preparation of the polymers, in addition, polymerization requires an initiator, whereas together with high temperature, high pressure. Whereas in condensation polymer, we do not require any initiators, are usually can be formed with much lower temperature, atmospheric pressure. Well, we have been talking about polymer properties. This difference between addition and condensation polymers lead to considerable variations in properties of polymers. Polymeric materials include plastic, fiber, elastomer. Polymers, since has grown, chemists and material scientists have learned how to develop new materials with particular properties. Following a few modification of properties of polymers include altering the average length of polymers, changing the structure of monomer, varying the extent of cross-linking between chain, selecting a monomer that produces a biodegradable polymer, producing a copolymer, making composite, adding fillers and pigments. Okay, most addition polymers are not biodegradable, but a recent development is that we can have use polyethanol, sometimes called polyvinyl alcohol, and polyethanol. Ethanol is used to make plastic bags that dissolves in water, and thereby it's biodegradable, and we can recycle these properties. Okay, now we are talking about a little bit organic synthesis. Not only organic synthesis, but synthesis. It's a pleasure studying why we have become so interested in the studying of chemistry. Why? For making new materials such as polymer, perfumes, drugs, dye, etc. So synthetic organic compounds are very important. And research production of new materials. Many features of modern life depend on the skilled chemist and their ability to synthesize new and complex materials. So for example, new colors, dyes, and fabrics in fashion industries are synthetic organic molecules. So also are the liquid crystals we use in flat screen of laptops and tablets and other materials. Essential goods. Well, we can major areas of chemical research today involves a synthetic drug and medicine. Okay, you see here is aspirin or paracetamol, which are synthesized, and it is potential drug to cure some or alleviate particular disease. For aspirin and paracetamol, this will relieve of pain. Salbutamol is salbutamol, which the IUPAC name of salbutamol is this RS4 2 tetrabutylamino 1 hydroxyl epsil and 2 hydroxymethylphenol. This prevents asthma. Okay. Chlorophenolic, this is the IUPAC name is this one. This is what is chlorophenol, and this can treat this medicine we can treat for typhoid. Levodopa, which is a medicine to alleviate Parkinson's disease. There are many other synthetic chemical research which involve catalysts, antiseptics, polymers, etc. Let us now consider anti-cancer drug, development of anti-cancer drug, which was developed in 1962. From what? From bark of the Pacific E tree. This is Pacific E tree, and we take the bark of this tree and then extract it, and we get some active compound, and that compound seems to be applied against ovarian cancer. But what I'm talking about, in 1962, it was reported. But then you see, we have to have about 2,000 trees to cut down and take the bark of those trees, and then can extract from there. We can get only 1 kg of Taxol. That is a trade name of this compound, which is acting against ovarian cancer. So this is a huge work, and we can fell down lots of trees for getting 1 kg. So people are always trying that it should be more economic viable, and then continuously doing research to see how we can minimize the cost of production, etc. So you see, 1962, it was on the bark. From there, they find the active compound is. And then you see, in 1971, so people are doing research and find out that, oh no, it is not we can also get the same type of compound from not from the bark, but from the, I would say from this part of the tree. Okay. So we developed this, and very slowly growing, and several trees had to be so that's what I am saying. Chemists had to find a way to make the drug from simpler substance. It took many years before a total synthesis was achieved. From the start, the project was planned in a great deal. The chemists do the understanding of mechanism of organic reactions and predict likely product at each stage and suggest rules of the target materials. So from the then in 1994, describing the successful 37 steps, and then from the needles of European E tree, we can make by only 4 steps reasonably commercially available Texas soap, and that it makes a lot of I would say cost-effective anti-cancer agent in Texas soap. So that what I want to mention, that organic synthesis, a continuous process to find out different types of compound which would be used in as a medicine, which will be used in many other fields. I mean, medicine and in other industrial organic materials and things like this. So we have to continue our research, and you see in 2002, the further development came, discovery of biochemical route for using the derived plant cell, and from there we also can find out the active ingredient of cancer. So that is a continuous process. We have to continue this. Well, I'll take another 3 or 4 minutes to complete the organic reactions. You see, we have been discussing about the reactions of more important reactions of alicyclic organic compounds, and we discussed in the last several lectures of AS and A-level courses. And here is a flow chart showing the very most important reactions, how it happens, what are the conditions to get it. For example, let's say halogen alkane. We can get it from alkanes. Why? How? With ultraviolet light, with halogen, room temperature and pressure, we can get halogen alkanes. And from halogen alkanes, we can get amines. So heat under pressure with ammonia and alcohol. So we can get amine. From alkenes, we can get halogen alkanes. That we have been discussed. Keep the halides at room temperature and pressure, we can get halogen alkanes. And not only that, alkanes. So this is how we can make a flow chart of to practice these reactions, aliphatic and alicyclic reactions, important reactions. Not only these flow chart, but we can also get reactions from the chapters and make our own flow chart like this, and keep it informed and look at it in regular interval. That makes you understand the reactions of organic synthesis and so, or organic reactions. Similarly, we can have a flow chart of benzene and its related compounds. Yes, as I say, this is aryl compounds. We have been discussing benzene and its derivatives. and mention many of these reactions in particular lectures. And then here is a flowchart to get the important reactions of benzene or aryl compounds. So take an example, let's say nitrobenzene is a nitrobenzene. We can get nitrobenzene phenylamine from nitrobenzene or reflux with ketene as a catalyst and concentrated hydrochloric acid followed by sodium hydroxide. So here are conditions from a compound to another compound, that's a reaction. So we have been looking. So I suggest that A-level student can have their own chart and keep this chart in a place where you can regularly check the chart and learn the reactions and their conditions and keep it, that will allow you to remember the synthetic route of various compounds and their chemical reactions. With this, I finish the AS level chemistry, that is the 45th lecture. And then one chapter is left, and that is the important chapter, the analytical instruments being used to analyze compounds and functional groups, etc. in the A-level chemistry. We take 2 or 3 lectures and add those instrumental techniques. We use our used to analyze compounds and what are the important notes to be taken while using analysis and deducting the conclusion. That's what we discuss in next 2 or 3 lectures, and thereby we will finish the AS and A-level chemistry present syllabus. Thank you very much for your attention.